DC electricity for future homes and DC grid with distributed renewable energy sources. So I would like to introduce speakers today. So for speakers, Prof. Taufik from California Polytechnic State University. Currently, he is full professor of electrical engineering from California Polytechnic State University, California, US, since 2009. And since 2011, he is the director of Electric Power Institute, California Polytechnic State University. It is his email address if you want to contact Prof. Taufik. So he obtained a bachelor degree, Bachelor of Science, Electrical Engineering and minor in Computer Science from Northern Arizona University in 1993. And in 1995, he obtained Master of Science, Electrical Engineering and Computer Science from University of Illinois at Chicago. And in 1999, he obtained Doctor of Engineering from Electrical Engineering, Cleveland State University. Currently, he is also chair of IEEE Power and Energy Society Chapter, Central Coast Sections, US. He was also section chair in 2004 until 2005, IEEE Central Coast Sections in US. So he received many awards and recognitions. So since 2005, he obtained Lockheed Martin Most Supportive Professor from Cal Poly. In 2005, he received Professor of the Year, Society of Hispanic Professional Engineers, Cal Poly. In 2014, he received Outstanding Professor from Cal Poly. In 2005 until 2006, he received Outstanding Faculty Advisor Award. In 2012, he obtained Outstanding Teaching Award from American Society of Engineering Education, Pacific Southwest Region. In 2013, he received Power Engineering Society Chapter Outstanding Engineer Award from IEEE Central Coast Sections. In 2018, he received Don and Paula He Annual Award for Outstanding Club Advisement. And also at the same year, he received Distinguished Scholarship Award from Cal Poly State University. And last year, he received Outstanding Achievement Award in recognition and appreciations of the research contributions to the field of power electronics from Las Vegas. He is also senior member at IEEE, and he is also a member of American Society of Engineering Education. So many awards and recognitions. Amazing. So, okay, welcome to participants online via Zoom and YouTube. You may interact and also write your question through Q&A in the box. Okay, I think that's all introductions about the speakers. Now I would like to invite Prof. Taufik to deliver talk. Prof. Taufik, time is yours.
Okay, Auzubillahiminasyaitonirrajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everybody.
Good morning.
Thank you very much,
Good morning for you.
Dr. Nia. Oh, yeah, oh, good. Yeah, it is evening here. Thank you very much for the very nice introduction, Dr. Nia. It is my honor to be invited for this talk. I will present my research that I have started since 2010, as Dr. Nia already mentioned, on the DC electricity and how it relates to future homes, as well as it relates to other applications as well. which hopefully trigger some interest to the participants today. That's the hope. For those of you who have not met me before, this is the first time we met, and I hope that this is not the end, but rather the beginning of hopefully long-lasting relationship between myself and you all. Okay, so that's the hope, inshallah. So then let me start sharing the presentation. Yeah, again, thank you for University of Indonesia, for Prof. Wisnu for inviting me to this event, as well as Dr. Nia for contacting me, as well as for putting this together for me. Thank you very much.
Yes.
Okay, let's see. Hopefully I can share. Can you see all? Can you all see?
Yes.
Yeah. Okay.
Slideshow.
All right. Slideshow. Yes. Where is it? Right here. Okay. And then laser point. Okay. Okay. Again, the topic of my presentation today is going to be on DC electricity for future homes and DC grid with distributed and renewable energy resources, or sources in this case. Again, my name is very short, Taufik. Hopefully it is easy to remember. It's a very common name in Indonesia, not very common in the US, especially in the US with only one name. That's also unique, you know. So make sure if you're planning to have a child, if you're married, planning to have a child, make sure you have two names. Name your child with two names, I should say, because in the US, you know, the system requires us to have two names, and so it's been giving me a lot of troubles having one name in a country that has a system that requires two names. So I can tell you all the funny stories, you know, in another opportunity maybe, but not today. Quickly about Cal Poly, since a lot of you probably have just met me today. It is a university located in California, founded in 1901 as a Polytechnic school, which was then converted into a university in 1972. However, our Polytechnic content of the program still remains, and so the name Polytechnic as well has been known in the state of California, so we didn't change the name to a different name, but rather keep the same one. We are a non-PhD granting school with about 22,000 students, second largest in terms of size in the state of California after Berkeley. And these are the different colleges that we have on campus, with engineering being the largest college, with about almost slightly over 6,000 students compared to the other colleges. And here's the location of the campus. We have the map of the US right here on the upper right corner. And then if you focus to the left, there's the state of California. That is like a long state. You know, it takes about maybe, I would say, 12 hours at least drive to drive from one end of the state to the other end of the state, north to south. So very long state. And then in the middle, right there, this is what we call the Central Coast area. That's where we at. That's where the campus is at, right there. Cal Poly State University is located very close to the beach, and it is located in vineyards, beautiful vineyards, mostly for tourists visiting, away from the hubbubs of the big cities. To the north of us, there's Silicon Valley. To the south of us, there's Los Angeles. And yeah, the middle portion right here is what we call, again, Central Coast section. So very beautiful place to live, but expensive as well. That's the downside. Here's the picture of the campus. 15 minutes away from the beach, and is surrounded by rolling hills. Right, this is buildings we have on campus. There's another angle of the campus right there. So imagine you have rolling hills surrounding the campus, and 15 minutes away, you can actually enjoy sunset on the beach, sunset on the beach. A beautiful place. And if I zoom into the middle of the campus, you probably can guess which of the building is the electrical engineering building. Anybody can guess? I'll give you the answer. It's this building right here. It's the backward letter E, right? That stands for electrical. So this is where all the labs are for the electrical engineering courses. And here's the building for the faculty of electrical engineering department. So I would like to extend my invitation to many of you to visit our campus one day. There have been quite a few Indonesian scholars who visit our campus to do short-term research, mostly 3 months, not just from Indonesia, also from the Philippines, from Malaysia, from Thailand. And they came here to work with me for research and do the short-term research. And we also went to conferences within the US while they are visiting. And there are also some groups from different universities in Indonesia who come to visit. And so I would invite as well, Professor Wisnu and University of Indonesia, Dr. Nia also to come to visit us, check out our campus, and hopefully someday we can also do some kind of a collaborations, do a short-term research of some type. So that's an invitation for all of you. This one is just showing the different ranking that we have in the US. This is the type of university ranking that is not being used around the globe. It's only used specifically in the US. It's called US News World and Report. So this is just one way of doing university ranking in universities in the US. So here is the different categories. The first one is the universities that offer PhDs. Right? So you can see for engineering, the top engineering schools out of 206 universities that offer PhDs for engineering. These are all very popular universities, right? MIT, Stanford, UC Berkeley, Georgia Tech, Caltech, and these are all world, renowned universities. But in addition to that, the same university ranking also have these different criteria. So the first one, the previous one was for universities with PhD, and the second one is top engineering school without a PhD program. And this is where Cal Poly is being categorized because again, we don't have PhD program. And you can see we are number 1, 2, 3, number 8, I believe. Number 8 in the country out of 1,829 universities. So we're, take proud of ourselves for this achievement of, getting the top 10 universities in the US for engineering school without PhD. So that's just a brief glance.
I'm sorry, Prof. Taufik.
Yes.
Maybe the screen is a double. Maybe can you customize, because we also deliver with the YouTube channel. When we see from the YouTube channel is quite small.
Oh, okay.
Can you?
Web interview.
Or maybe just like this. Is that okay?
A slideshow.
Or slideshow?
Yeah.
And then?
And try to swipe presenter in display setting. Try to swipe presenter, maybe. Yeah.
Oh.
Yes.
Okay, perfect.
Okay.
Perfect.
Okay.
Thank you. Prof.
I'm sorry. Sorry about that. Thank you for letting me know.
Because we are also live streaming on YouTube channel now.
Oh, wow. Okay. That got me nervous.
Okay.
All right.
Yeah, it's
Very
okay.
good.
Yeah. Please
Okay.
continue.
All right. So these are outlines of my presentation. I'll start with why DC. Right? So let's have a look. I have these three examples, just three, right? Out of so many portable electronics that people use these days, right? I have smartphones on the left right here, and I have LED lights, and then I have oh, hang on a second. I also have, there you go. I have tablets right here. So these are graphics or graphs that show the increasing use of these devices over the years. You can see from 2006 to 2021 as an example. And all of them, show the same thing, that the number is increasing throughout the year. And why this is important, I started the project in 2011 or 2010. Early in 2010, before 2010, I follow closely all these statistics that I saw that they are increasing in numbers. The use of these different devices are increasing in numbers, and so that's the reason why I predicted that DC loads are going to be increasing. And why this relates to DC loads? Well, as you know, smartphones, even though you are charging it into the wall plug at home, but internally, smartphone is operating with DC, right, with battery. So battery is a DC source. LED lights, same way. LED lights is also operating with DC, not AC. But the way we use it these days is that we plug in our LED lights into our AC system. Same thing with tablets, right? Even though internally, or not internally, even though you're charging it through AC, but internally it is actually DC. So all of these are examples of DC loads that we often connect to a wall plug at home, AC wall plug at home. So these are all internally DCs, and therefore any power that is supplying into these devices will have to be converted into DC. Now, how much energy is being processed through these devices? If you just look at one smartphone, it's not much, right? But if you look at globally, for example, I'm just going to take a smartphone as an example. There are 2 billions. There will be 2 billion smartphone in the world by 2021. And let's say that as you are plugging a smartphone into the wall to charge, let's say that voltage when you charge is 5 volts. And let's say that the amount of current that you are using to charge is 1 amp. And let's say it takes 1 hour to charge it. And there are 2 billions in the world. Now you can do the simple math, and you can end up with so many zeros, right? Look at that. 10 gigawatt hours of energy being processed into DC. So now you see, relatively speaking, now you see the amount is staggering, right? You can see that it's huge energy being processed into DC, 10 gigawatt hours per year, or 10 gigawatt hours per charge, all out of these 2 billion smartphones. Imagine if I add the LEDs and the tablets and other things that you are using at home, right? So it's going to be so much energy being processed through DC. Another thing is that we have this technology that came about around 2015 out of Intel when they launched USB Type-C, which I'm sure many of you are aware already, right? Many smartphones nowadays are using USB-C to do the charging, right? Instead of USB 3.0, now it's USB Type-C. Now, USB Type-C has many interesting features, but as a person with a background in power electronics, my interest is looking at this one number right here, more power, right? What it means is that the target for USB-C is to be able to supply all the way up to 100 watts. Imagine that. So imagine this USB-C cable that we have these days. In the future, we'll be able to exchange or accommodate or facilitate processing of energy or processing of power, I should say, of up to 100 watts, right? So that means in the future, this USB-C would be able to power bigger devices in our houses, in our homes, right? So imagine a small refrigerator being powered by USB. Imagine, TVs being powered by USBs instead of the conventional AC that we are using these days. And I did a little bit of a rough estimation some time ago in terms of the mix between AC and DC loads at homes. And this is based on average US homes, average house in the US. On the left, around year 2000, the mix is about maybe 30%-ish, right? About 30%, maybe. So right here, so you can see the portion of AC loads and DC loads. DC load is taking up about this much out of the total loads. You can see that DC loads right here is mainly coming from TV, laptop, and desktop, whereas in this, that's not 30%, that's about 20%, sorry. And if you go to the right there, right, year 2018, the portion increases, right, to maybe around 30%, so from 20% to 30%, and roughly. And these days, we have more DC type loads, such as smartphones, tablets, LED TVs, LED lights, laptop, desktop, and so on and so forth. And this mix right here, the mixture between AC and DC, I would argue that in developing countries such as Indonesia would be better when it comes to DC, meaning the portion of the DC would probably be better, would be bigger in developing countries. The reason being in developing countries and also culturally we are different. If you look at an average house in the US, every house typically has a big fridge and air conditioning. These are all big loads, and also big washing machine and big dryers, right? But in Indonesia, for example, on average, in every house, if they have any refrigerator, it's going to be a smaller refrigerator, and probably not every house has air conditioning as well as washing machines. So as you can see, from those different type of loads, the DC mix in developing countries should be bigger than the developed countries. So then, what is the big deal about having or knowing that the DC loads are increasing? Well, the big problem here is that we have a mismatching between source and load, right? A smartphone, for example, as I mentioned earlier, internally is running DC because there's a battery inside, right? So it's powered by battery. But then when you are charging it into a wall plug, we know that a wall plug puts out AC. So therefore, you have to do this process of converting AC to DC. And when it comes to converting from one signal to the other signal, we have to realize that there is loss associated with this conversion. And this loss could be big, right? It could be significant. It could be between 17 to 35% loss. And so if you are processing 100 watts, then 35 watts, between 17 watts to 35 watts will be lost as heat, right? So that's not good, right? At the end of the day, you're paying for this load, for this loss, right? You're paying more money. because of this loss. Right? So we got to do something. We have to do something better than this. Right? And this loss, if you feel like, okay, 17 to 35%, that might be something that we can tolerate. Well, hang on a second there, because if I do rough estimation of the significance of this loss, then I'm just gonna do 5% to demonstrate how significant this percentage loss is. Right? Instead of using 17 to 35, I'm just gonna use 5%. Let's just say that the loss is only 5%, which is much smaller than 17%, right? Let's just say. And I'm just going to use two examples, a tablet and a smartphone, right? So throughout the year, right, on average, a tablet consumes about 12 kilowatt hours per year. And based on the curve that I have previously, there was about 760 million tablets in 2016. Right. So imagine that if every single tablet consumed this much energy per year, and there's this many tablets in 2016, and go ahead and multiply these numbers, right? And you get energy used per year, right? Globally by these tablets. And if I can just save 5% of that, then this number gives us pretty significant number. Right, so 5% of these numbers is 480 gigawatt hours per year. Not a tiny number anymore, right? You can see that from the 5% loss, we get 480 gigawatt hours per year, right, throughout the world. If I use another example, smartphone, which consumes on average about 4.2 kilowatt hour per year, and there's about 2.71 billions in 2019. Then go ahead and multiply these numbers and then times 5% to represent the loss. That would give you also a big number. See that? 599 gigawatt hour per year. Again, this is not a small number. If you just add the two numbers, this is again coming from the loss. You add the two. And the number, when you add the two, is equivalent to having 12 units of 10 megawatts power plants operating 24/7 for the entire year. And that's amazing that this 5% loss could actually save us from, if somehow we can get rid of this, it will save us from building 12 units of 10 megawatt power plants. Right? Lots of money being saved there. Not only that, but we're creating a cleaner environment if you could somehow save that 5%. Another thing that's a big deal about DC is that more and more people are using renewables, in particular PVs, right? They're putting more and more rooftop solar panels on their house, right? And as we know, PVs, these are all DC power, DC source, so it's putting out DC, right? So then if our source is already DC and we have increasing number of DC loads, then it would make sense to me that the way we process the energy is from DC to DC, right? Unlike the way we're doing it now, right? This is how we do it now. If you have a PV rooftop on the rooftop of your house, then that PVs will give out DC, and that DC will have to be converted to AC, right, into your house. And then if you are plugging in a smartphone is DC, then that AC has to be converted to DC. And out of the DC, you have to regulate that DC even more, right, to another DC. And then you can use that energy. You see, you have the difference between having just one single stage process versus 3 different stages that we have currently, right? And every single stage will have loss, right? So as you can see here, from converting DC to AC, you're going to be encountering between 23 to 28% loss, not a small loss. And then from AC to DC, I've already give you this number. That's 17 to 35% loss. And DC to DC could be very efficient. It could be giving you maybe around 3 to 5% loss, right? So again, it would make sense to me and hopefully to us that in the future, right, when we have more and more DC loads in our house, wouldn't it better if we can have a system that would facilitate these DC loads straight from a DC source, right? If we have the DC source, or if not, then we should do from AC to DC and then straight into DC instead of this current technology that we have these days, which is very lossy. Right? And then another thing is since more and more people are using renewable energy, then this presents an opportunity for us to be able to develop technologies that would help our brothers and sisters around the world who are still not having the access to electricity. There's approximately about 1 billion people still live in the world without electricity. And ironically, people who don't have this electricity live in the areas where there are so much renewable energy sources available around them. It's very ironic that they have all of these energy sources around them, but then there is a very minimum amount of technology that could, enables them to use or to tap those energy. So we can be part of this. We can be part of this movement to help, again, increase the use of electricity around the globe. Right, I'm also speaking of Indonesia. As you can see the picture at night, the satellite picture at night. You can see that Java is the only island that's very bright compared to the rest of the islands in Indonesia. So we need to do something about this, right? We need to increase rural electrification ratio, right? The actual electrification ratio, not the numbers that we get from PLN, but the actual availability of electricity on these other islands besides Java. So we could do this. We could definitely help this by developing the right technology for them, for our brothers and sisters living in other islands. And so DC could provide an improved solution for off-grid rural electrifications, because with DC technology, you don't need to have big hydropower or wind generator, right? It's a much simpler lighting system, as an example, or overall is going to be a much simpler DC electrical systems. Lighting system is just an example, right? You can have an LED lights, right, being powered by a simple solar panel plus energy storage system, right? That way we could prevent kids from using kerosene lamps to study, like this picture on the left. Believe it or not, I grew up experiencing this right here. Maybe many of you, did not have this experience, but I did. Even though I was born in Jakarta, but early 1970s, when I was still in elementary school, there was no electricity in our house back then. So I still remember studying every night, doing homework, I should say, every night around these unhealthy kerosene lamps, right? Or, in Indonesia, we call it lampu semprong, right? It's very unhealthy, right? We inhale all of these gas that is unhealthy for us to breathe in. And, convert this unhealthy kerosene lamp into, smiles, right? Imagine if you can somehow replace this kerosene lamp with a simple DC light, right? That could help, bring smiles to these kids, right? It doesn't matter whether or not they live in Indonesia, but this is something that us as engineers, we need to contribute to humanity, right? So it doesn't matter if whether or not they live in Indonesia or outside of Indonesia. If we can contribute to something like this, that will be a great contribution from us. All right. So then, residential DC electricity, that's the topic of today's talk. As I said, one of the systems that there are many, of course, different ways of doing this. But the one that I started at Cal Poly is what I call DC House. I started in 2010 to develop a residential DC electrical system. The initial goal was to develop an alternative solution to existing rural electrification technologies. We're doing it by direct use of DC electricity with DC loads. And we want to provide seamless integration of one or more small-scale renewable energy sources, right? And we also would like to expand from previous ideas, of having a purely DC system. So I'm not going to take any credits for DC system because that's been around for a long time. You probably heard about Edison system, which is also a DC system. So what I'm trying to do here is I'm trying to expand these previous ideas, make it more comprehensive solution, scalable, reliable, etc., in utilizing multiple small-scale renewable energy sources. And the approach that I'm taking is different from existing rural electrification technology, right? Which is typically top-down. What I'm doing is bottom-up. It's totally the opposite. Right, so start from small scale and grow from there, right? So instead of start from a big system, I'm starting from the other end of spectrum. I'm starting from the small scale of electrical system. So on the smaller scale, a DC house system could be just a solar lighting box, which is being commercially sold these days. This was an idea in 2010, but 10 years later, many companies are selling this, believe it or not. They're selling a box that has, solar cells around it. And then there's an LED lights and USB, what have you, in the box. So that during the day, they would just put this box outside under the sun. And then at nighttime, they would bring this box inside and that would power their lights as well as their charging their devices. On a residential scale, a DC house system is a standalone off-the-grid house. So you want this to be a system that helps people living in remote areas, isolated areas, right away from the grid, and make use of multiple small-scale renewable energy sources. And then on a bigger scale, a DC house system would also be a network of locally powered DC houses. Okay? So that you can see there's a different levels of capacity of these system, but starting from small to big, depending on how much the people can afford to put the system. If they cannot afford to buy a big system, then why not provide a smaller system for them? So that's basically the philosophy that I'm using when it comes to rural electrification, is that one size does not fit all. Right? We just having one technology for rural electrification is not enough, because this technology that we have today, and I'm not saying bad about them, these are all very good technologies. Hydropower, solar farm, wind farm, what have you. These are all great technologies, but unfortunately, these technologies may not be suitable for many other areas, right? In islands, for example, in remote villages, it may not be suitable for them. So therefore, we need to come up with an alternative solution for this, right? And so that's what we've been trying to do, is that we are trying to offer a different option for rural electrifications. So small scale, more adaptive solution that is reliable, scalable, multiple, expandable, reachable, and flexible. So many features. So reliable means every house will have their own local energy source. Scalable, power capacity would be adjusted per needed basis. So remember, bottom up. So we don't want to force every house to have 600 watts, for example. We should leave it up to them, right? If they can only afford 10 watts and they are interested in using 50 watts, for example, then give that to them. Don't force them to use 600 watts as an example. Multiple. Every house may have more than one energy sources, not just one. It could be more than one source. Expandable. Accommodates electrical network of several nearby houses to form a local grid. We'll talk about it later. Reachable. Utilizes renewable energy sources, which is crucial for areas unreachable by the main grid. And flexible, meaning that this system should be flexible enough to be able to accommodate the existing system as well. A mix between AC and DC. Wouldn't that be wonderful if we can have such technology? And this is what we're trying to do. This is the schematic of residential scale. There are three different components. We have the the generation scale right here. So every single house could have more than one. And please keep in mind that more than one sources, I should say. Keep in mind that every single source here is small, not big. So small sources. So we want to be able to tap small energy sources around this house and combine them into a single DC bus to power the DC loads, right? So a good example would be maybe there's a village where there is no big rivers running close to them, in which case it is not suitable for micro hydro because it's too small for a micro hydro system. So then why not, right? Why not utilize this small river, right? Small stream. So then combine this with a sunlight or solar panel. Right? So the small hydropower energy with a small PV into single DC bus to power, a small DC house system, something like that, right? And in the middle, we have this interface, which is the key technology to be able to utilize, these multiple small sources of energy. And this is what I call miso, which is a familiar name for Japanese soup. But that miso right there is actually short for multiple input, single output, because we have multiple inputs, right? 1, 2, 3, 4, however many, and single output on the other side. And that's why I call that miso. And just briefly, this is on the generator side. There's a lot of development on that generator side. I won't go through this, but imagine a small stream of water right there, which is not suitable for hydropower, but you can still use a small, water generator or hydropower generator such as this one, portable nano hydro power. Just dip it underwater and it'll spin and it'll not big but small, but it doesn't matter, right? Small is still useful into the DC house. And then we also develop play park generators. You have swings for kids to play, seesaw, as well as merry-go-round for kids to play. So while the kids are playing, we can also get the energy out of the kids, right? And out of our children, and also exercising machine too, right? If we want to exercise using bicycle, right? Human power generators will be another way to do it. All right, so since many of you are computer science major, I'm trying to think of what kind of things relate to the software side of these project. So definitely one of the helps that we can get from the computer science community is having the software to be able to manage all of this energy flow in the system, because it's quite a complex system, right? As of today, we don't really implement this controller, just all robust, control, manual control. But it'll be nice to be able to have something like this, right? Software-based controller for residential, based DC house, right? So you have a part of the central controller energy management system, basically, right? So energy management control and monitoring system, a part of it that would monitor and control sources, right? And then another part that would control and monitor energy storage, and another part that would control and manage or monitor the loads. And all of this information is being fed into a central controller that would make the right decision of what needs to be done per given condition, right? So, for example, if the energy storage is low, but these the house is demanding a lot of energy, and at the time we have plenty amount of energy here, then you shut it off. You can shut off the battery from supplying energy, but rather charging it, right? So you can charge the battery and have the energy to flow from the sources straight into the house and to the battery, right? And so I'm sure there's more that you can do out of this. For example, if there's not enough energy from the source, and we have all the loads running, then this controller right there, the load manager, will be able to determine which of these loads are critical loads, right? So if we don't have enough energy, then we can start do a load shedding type of approach, trying to shut off loads that are not really critical to the house. And this needs or requires, it will be better if we can have software doing it instead of manual control. So I'm sure there's a lot to do this, and you can also introduce an HMI type of display or interface, I should say, right? Human machine interface or a mobile app. You can have an app on the phone that can actually do this management of energy flowing in the system. And yeah, so right now, this is what we have in terms of energy management system. These are all hardware, not much software. It's not really a smart management system for now. It's still a lot of wires, right? So it'll be great if we can get more help from software engineers to develop that kind of capability. And there's the multiple input single output converter, the key technology. After 8 years, we were able to find the key, and this is basically the hardware that would enable us to combine multiple sources into one single output, right? And I received the U.S. patent last year for this technology. More stuff for us to develop. One thing that would be related to maybe software side is what's called smart wall plug. I do have other things right there, but these are all more on the hardware side. But on the software side, imagine we can have a smart wall plug. What is a smart wall plug? Well, one problem with DC is that DC is not standardized, unlike AC, right? In your house, you have AC. Whenever you buy any appliances for your house, it's already standard 220 volt AC, right? So these are all standard voltage. But DC, there is no standard yet, which is good and bad, right? It's good because then there's plenty of room for us to explore, but bad because then we have to determine how we can deal with different type of loads, different type of DC loads, right? So DC loads is not standardized. Some DC loads are running 5 volts, such as USB type DC loads, right? Some loads are running 12 volts, very common, 12 volts DC. Some loads are running 9 volts, as well as 24 volts. The bigger DC loads, they, of course, running at higher voltage, right? So what would you do imagine if you have different DC loads, right? 5 volts, 9 volts, 12 volts, 15 volts, 24 volts. Are you going to provide multiple wall plugs in the house? That would be ridiculous, right? That would be absurd to have. So to me, that's not a good solution. A good solution is to have just one wall plug. That way it's not confusing, right? Imagine if we have multiple wall plugs and we put it in a remote village. These people, they're probably going to get confused, which wall plug they're going to have to connect their DC load into, right? So a smart solution would be to have a smart wall plug, just like this, right? You have one smart wall plug, you plug in the load, right? Doesn't matter what voltage it is. This wall plug will be able to find that voltage. So if the load connected requires 15 volts, then the DC plug will find that voltage for you, right? So in order to do this, we need hardware and software. And there's the hardware right there. It's done. The hardware, we already done it. But what's not completed is the software side. Because again, we are not a computer scientist. We are electrical engineers. We do our best when it comes to putting the right algorithm for finding the voltage. But I bet you many students here today, many computer science students today, would probably be coming up with a much better solution than what we did. So go ahead and if you're interested, go ahead and look into this and help us in terms of finding the right algorithm, developing the right algorithm to come up with the more accurate target voltage algorithm. So right now we were able to do this, but I'm still not happy. I'm still not satisfied with our algorithm, because every time we plug in a DC load, it can only achieve voltage at slightly lower than the targeted voltage. So for example, if we plug in a 12 volt load, then this algorithm that we developed can only get to maybe 11.8 or something like that. So it's not really accurate, and I'm not really happy yet. I'm not satisfied yet, because if the voltage is lower, that means it's going to draw more current. If we are drawing more current, that means the system is not efficient. So that's why I'm not satisfied yet of our current solution. And then the other aspect of the presentation is having a DC grid. So another extension of a DC house, residential DC house, is residential DC grid. And this will be very useful when we have villages with clustered, houses like these right here. This picture, these are all in Indonesia. Flores Island, I don't remember where else, maybe NTT, right, Nusa Tenggara Timur, where we have a cluster of houses, just like that. Imagine if you have clustered houses like this, then it would be good to be able to network, because they're so close to one another, right? So why not network this so that we have an improved version of DC system, right? And of course, when it comes to a network of DC houses, then you still need software to be able to manage energy flow from one house to another house, right? So that's another thing that people who have background in computer science could help us with, develop this controller, right? Grid controller for this DC house network. Right? That's something that we have not developed yet. So there you go. You have more ideas to develop or to help this project. And this is what I'm actually proposing, right, to the left. Again, I'm not saying that, one more time, I'm not saying that current technology is bad. I'm just saying that, for some condition, it's not suitable to use current technology. So on the left, we have centralized micro hydro, or wind turbine, or solar power, solar farms, what have you. On the right side, we have the proposed DC grid network with DC house. So every single house here is a DC house. Imagine every single house has multiple sources, as well as, or maybe only one source, what have you, right? So let's see the difference. If you have a micro hydro, centralized micro hydro technology, one disadvantage is that if the source is down, then the entire village will be dark, right? If the power station is down, then every single house is dark as well, right? And then if the main bus between power station to the houses is broken somehow, then of course all of these houses will be dark as well. All goes to dark, right? All go to dark. So then same thing here. If let's say the top portion of the line is down, then the houses connected to the top line will be down as well, right? So you can see there is a disadvantage of using centralized approach is that reliability, right, has to be sacrificed there. But what I'm proposing is this right here, right? So what happens if, so you can see this is distributed energy source, right? So we have many houses, and every single house is a DC house that have multiple or just one source, just like that, right? So what happens if that solar panel is down? Is that house going to be dark? Of course not, right? Because the energy could be supplied from other houses, right? If, of course, the energy is enough to do that, right? And what if we have the situation where the line going into that house is broken? Well, that house right there should be good as well because it has its own source. It's not centralized, right? What if we have that portion of the line broken? Then, of course, the top houses will still be having lights at night, right? Because they have their own sources. So you see that by using this proposed or alternate solution using DC grid, right, we can improve reliability of our system, our electrical system, right? So that's the DC grid. Now, what about future homes? This is another exciting exploration that I started about 2 years ago. I'm still doing this now because every time I'm doing a presentation on DC house, people are always interested in having the DC house system for urban area, right? For houses in big cities. So I told them that for big cities or urban areas, you can still use the DC house system. However, the goal will be different, right? Initially, the goal is to provide access to electricity in rural areas, but in urban areas, it's going to be different because they already have access to electricity. So what you can do here is that you can adopt a DC house system for hybrid AC/DC, right? So a hybrid AC/DC whose purpose is to reduce electric bill, minimize the cost of using electricity from PLN, or even become independent, right, at a certain time from PLN, right? So that could be done by having a system that looks something like this. Right? This is still a concept that we are developing at Cal Poly, right? I have a master's student looking into this right now. And you can see that we have two different sources. As an example, we have one source from PLN, the other source from solar panels, rooftop, let's say, right? And PLN is outputting AC or providing AC, whereas solar panels outputting DC. So we have two lines here, AC and DC lines, right? And then from AC lines, we can, from the PLN, we can have a line straight, powering our big AC loads. So if your house has air conditioning, washing machines, that could be connected straight from PLN, right? Just like that, because these are all big loads. But what about LED lights? LED lights are all DC. It does not make sense for you to plug in your LED lights into the AC line there, right? So why not for LED lights, you have the DC line right there, and it goes straight into the MISO, right, to combine with other sources, and then connect your LED lights through the DC line right there. So now you have AC distribution system and DC distribution system that would facilitate the DC loads, right? And then you can see there's crisscrossing between the two. So from DC, you can also convert to AC as a backup. So just in case, PLN goes dark and PLN, you shut off their power, right? So blackout, let's say, from PLN, then you can still power your AC loads through the DC line, right? Either from the solar panel or from the battery right there through this inverter, right? Likewise, if let's say that the solar panel somehow, there's monsoon season, right? So rains every day, not much solar lights, not much solar power, then your DC load could still be powered from PLN, right? Through this path right there. So from AC, it goes into a power supply to convert into DC, and it goes into MISO, and it powers your DC lightings right there, right? So you can see how much improvement we have by having this AC-DC mix of system in our house. And to me, my projection is that in the future, our home is going to be like this. Right? It's going to be a variation, if not going to be like this. It's going to be some kind of AC-DC mix electrical system in our house in the future. Again, DC system is being used in many devices. I've already mentioned it many times. But if you want to have a smart home, for example, a smart home is a home that has so many sensors inside the house to do whatever it is that you want to do, right? Monitors different aspects of the house. Then, as you know, sensors are running in DC. So imagine if your house is already has DC system within it, then integrating sensors will be easy, right? Would be straightforward. Same thing with net zero energy building right there. How do you accomplish a net zero energy building to make a cleaner environment? And that requires a lot of DC architecture inside the house. So by developing the technology, then we have the capability to pursue this technology in the future. Now, again, from software side, this is just an example. This is actually a real picture that I screenshotted from a website. I'm currently working with on a project with a company that basically does this in the future. Does this AC/DC mix. This company already put out the software mobile app. So through a smartphone, you can control the different portion or monitor different portion of the house. This is the part that I would not be able to do. I think computer scientists will be able to develop this kind of apps. And you can see in that house, we have 4 different components: solar panel, battery, the house itself, and the grid from PLN. And it'll show you how much power is being exchanged at any single time. You can see the numbers there. So if you look at the picture on the left, at this moment, we have 5.72 kilowatts being received from the solar panel. And then the house itself is consuming 3.2 kilowatts at the time. And the energy storage is enough to provide 12 hours of energy. And so the excess energy from the solar panel goes into the grid right there. So 2.5 kilowatt is being absorbed by the grid. Right, and then there's different functions of the system. There's a backup function for the energy storage, the self-supply, and so on and so forth. And this is also nice, right? Basically, gathering data, right, and making it so that it's useful for a user to see. You can see the different graphs that shows the different components in the system. Yellow, I believe, is solar panel. Blue, I believe, is the grid. Green is the energy storage, and pinkish is the house, right? So you can see clearly from here, as an example, watch. As you can see from the yellow curve, you can see that the yellow curve, which represents solar panel, start to go up at this time. So I know this is where the sun starts to rise, right here. And this is about maybe around noontime, where we have the maximum amount of energy from the sun. But you can see, how energy flows, back and forth between different components in the device, in the components, in the house, from these components. And this will be a useful, data for us to see. And again, these are all, software-based kind of tool. All right. Another thing that I don't have the time to include here is another project that I'm doing currently. Where we look at how to integrate a GIS system to be able to help people size their solar panels or size their energy storage as well. So imagine if you have, GIS system, and every GIS system has, so many information regarding, geographical information, longitude, latitude, right, and all of those. And based on this information, we can then determine what kind of a solar panel size that would be required for the house, and how much energy storage being required for the house to be able to, minimize the amount of electric bill they pay every month, right? So that's another development that I believe, would be of most interest to software engineers, such as, many participants today. And these are just pictures to show the different prototypes we have around the world. I have a prototype of the DC house at Cal Poly, at Pajajaran University, Philippines, and then this is the Regency kantor kecamatan di Jatinangor. Still an ongoing project. It's a huge undertaking. This project, requires, huge undertaking, and we're not even halfway. And as an electrical engineer, I focus more on hardware development, not much on software. So if you're interested in the software side of this project, definitely we need to work together if you are interested. So as a summary, DC, I'm just gonna make it shorter because this is kind of long. So DC house is a concept that enables us to leverage DC technologies, and is ever evolving, starting from rural areas into smart homes, as well as hybrid AC DC house for future homes. And another way to explore the DC technologies by having a DC grid, making network of these DC houses. And basically what I'm trying to say here is that, I'm just going to end it right now, is that there's so many opportunities for people whose background is in software to be able to contribute to this project, right? I mentioned several things earlier, right? Energy management systems for the residential DC house, for the DC grid, for AC DC hybrid, for a smart wall plug, and I'm pretty sure there's more other things that that people can help out on the software side of these project. So anyhow, I want to stop right here because I want to give a chance for participants to ask questions. And there's the website for the DC house if you're interested, right? dchouse.calpoly.edu. And that would conclude my presentation for today. I'm going to stop sharing now.
Okay, thank you very much, Prof. Taufik, for interesting talks. Yeah, I noticed there are many great opportunities for us in computer science. I mean, because I'm computer science, to join in these projects. Okay, we received so many questions here in Q&A box. Hello, Prof. Taufik.
Yes.
Oh, okay. Because I saw that your video is freezing.
I'm having problem with my laptop. I need a new laptop.
I see. All right. Okay. So now I'm going to read one by one questions in the Q&A. So from Mr. Waluyo. So at home, usually we use 220 volt for AC voltage. About DC, what is the best voltage used? Because in DC circuits, the DC voltage is very dangerous compared to AC voltage at the same nominal voltage. So what do you think, Prof. Taufik?
Yeah, should I answer right now or?
Yes, please.
Yeah, so that's the wonderful thing about exploring DC is that, as I said in the presentation, there was no standard for DC. So back in 2011, I had two students looking into this problem. The exact question you have, Mr. Waluyo, is that what kind of voltage should we use for the DC electricity, at least for residential scale? So I have two students doing the study independently. And what's interesting is that at the end, both came back to me and said that 48 volt is the best. And so that's what we used since then. We use 48 volts. And if you've been reading on DC technology these days, which is again growing fast, industry has also converged into a single DC voltage. And guess what that voltage is? It's also 48 volts. So we were so happy that our study agrees with what industry is actually converging these days, 48 volts. But please keep in mind that 48 volt is based on residential scale. If you are doing network of DC houses, such as DC grid, then the voltage is going to be larger. I don't think it's going to be 48. It's going to be higher. Otherwise, it's going to be inefficient to use 48. Yeah.
All right. Okay, thank you. And now I'm going to read the questions from Mr. Daeng Supriyadi, my colleague from Polynes. So how effective the systems for supplying such as residential heating and cooling loads? How effective the system?
Heating and cooling. I think for heating and cooling, there's still ways to go for DC, even though the technology is it's catching up. When it comes to machines, I'm not an expert in electric machines, but my colleague who is told me that nowadays, DC brushless machine is becoming more efficient. So the technology is not quite there yet. And so when it comes to DC, I think for heating and cooling, DC is still not as efficient. That's why just stick with AC for now for heating and cooling, meaning use AC machines, AC electric machines such as induction motors. Those are still efficient, more efficient than DC machines. But it's getting there. It's getting there. So it's not that that DC is not going to be happening for cooling and heating. It is happening. If you can actually Google this, and there's actually companies. There are companies in the U.S. and Canada, for example, who are right now building solar-powered refrigerator and solar-powered air conditioning, all kinds. So they're already building these appliances already. So yeah, it's coming. It's coming.
I see. All right. Okay. So thank you. So for the next questions from Mr. Arina Friel. Oh, actually there are.
Mbak Nia, I think Prof. Taufik, because your presentation is very wonderful and very interesting. Many attenders give the question, but I think the question is we can cluster maybe Mbak Nia, so that maybe not every question we must answer, but maybe it's up to you Mbak Nia. But this is my point. Okay, thank you.
Okay, yeah, I will try to read and make categories for the similar questions. Okay. So, will the DC house be able Indonesian government to help minimizing issues with intermittency of renewable energy sources? And in the future, is it planned that the DC house will extend its functions as a disaster relief house to provide electricity for affected people in the rural area? So what do you think?
Yeah. So that is the goal, right? That is the goal. That's why we have developed this technology so that it enables us to use multiple, not just one, but multiple sources. So by having multiple sources, and they're not big, right? We don't require big sources. These are all small scale. It could be big too. So it's very flexible. But the point is, you can put multiple sources and combine these multiple sources into one. So that's addressing the issue of intermittency, right? So if one goes down, the other one still is up, and you can still have electricity going into the house. So that is actually the part of the goal, to get rid of or to improve intermittency of renewable energy system that we have these days. And the disaster relief house, I don't think I have it on the slide, but in the previous presentation I did for another university, I actually have a slide on disaster relief house using DC house system. Because another thing that you can develop with DC house system is that you can have like a ready to use electrical systems. Imagine if there's a disaster, a natural disaster hitting an area, and you bring in your disaster relief house, and we want to be able to install, set up electrical system fast. And that could be done with DC, right? Without having generators, all of these hassles. You can just have, solar panels. And nowadays we have, a flexible solar panel that you can just roll up, right? Just bring it to the roof of this relief house, and you got electricity fast. So exactly another application of DC house system is for disaster relief house. So hopefully that's what Indonesian government would like to get involved. But so far, no, though, unfortunately. So far, I don't have any. I don't receive any interest from the Indonesian government.
Oh, okay.
Yet.
Okay, thank you. So, questions coming from Dr. Risnandar from LIPI, I think. As you explained, Prof. Taufik, how to get DC-DC or AC-DC or MISO in Indonesia? Maybe do you have any recommendations?
Yes. Yeah, no, I'll be more than happy to develop the technology with whoever it is interested. I mean, there are simpler way of doing this, and there are more advanced way of doing this. So the one that I received patent for, the U.S. patent, that was the advanced way of doing MISO. But there is very simple way of doing this as well, and I'll be more than happy to share that info free of charge. I'm not even going to charge, right? If you're interested, Dr. Risnandar, go ahead and contact me, and I'll be more than happy to share the info so we can have MISO or whatever it is that you need to establish this DC technology.
Oh yes, okay. Do we still have time? I think, Pak Wisnu, 10 minutes more.
Maybe 10 minutes more. Prof. Taufik, as we discussed from the beginning in the course, because many attender is not many majority is from Indonesia. I don't know. Maybe because you are stay in US for more than 20 years, maybe. So how about your Indonesia, your bahasa? Maybe can you explain in bahasa, maybe, or
maybe you summarize a little in bahasa Indonesia, Prof. Taufik?
And also the
most
attender,
participants are Indonesian people, but also some of them from.
Okay.
And how about the attender who want to give you question in bahasa is okay, maybe?
Yeah, okay.
Request from. Okay.
I saw some participant send questions in bahasa Indonesia.
Ya, nggak apa-apa, silakan.
Oke, mungkin Prof. Taufik bisa beri short summarize in bahasa Indonesia.
Oh gitu, ya. Ya, jadi intinya teknologi DC ini saya kembangkan karena saya melihat potensi listrik DC di masa depan. Ya, akan adanya perkembangan yang pesat di teknologi DC, ya, yang terutama hubungannya ke yang beban DC. Dan kalau untuk sumbernya itu berasal kebanyakan dari solar panel. Ya, jadi ada pertumbuhan dalam pemakaian solar panel yang memproduksi DC dan peningkatan jenis beban DC. Jadi kalau sebagai orang elektro tentunya saya melihat ini sebagai satu kesempatan emas ya bagi kita supaya bisa mengembangkan teknologi yang bisa membuat matching antara keduanya. Jadi jangan lagi kita pakai perantara AC, langsung saja dari DC ke DC, apalagi nanti kalau hubungannya ke rumah masa depan, di mana bauran antara beban DC dengan sumber DC akan lebih tinggi lagi. Tidak masuk akal bagi saya kalau di rumah masa mendatang masih tetap pakai AC saja. Ya, AC bukan air conditioning ya, sistem AC. Ya, tapi harus ada DC-nya juga. Jadi seperti saya sudah gambarkan tadi sebagai rangkuman bagi saya pribadi, rumah masa depan itu akan terdiri dari 2 jaringan di dalamnya, yaitu jaringan AC dan jaringan DC. Nah, seperti itu. Dan aplikasinya tentu semakin ke sana semakin banyak, termasuk aplikasi smart house, aplikasi the grid ya, DC grid dan sebagainya. Mungkin itu aja summary dari saya.
Oh, baik, Prof. Taufik. Ini nggak bisa benar-benar kelihatan videonya ya, Pak?
Oh, nggak bisa ngeliat video saya?
Nggak bisa.
Oh iya, kalau soalnya ini nggak tahu nih, saya juga laptopnya lagi ngadat.
I see.
Yeah.
Okay. So one more questions from Bapak Mulyono.
Maybe directly Mbak Nia. The attendee, we will upgrade the attendee become panelist. So maybe they can discuss directly with the Professor Taufik. Okay.
Oh yes. Mungkin bisa di-upgrade Pak Mulyono Wijaya, atau mungkin tadi Pak Risnandar dari LIPI mungkin ingin bertanya lebih detail. Ini ada
video
pertanyaan.
Saya sudah kelihatan belum?
Sudah sekarang.
Oke, ya.
So what happened just now?
Ya itu tadi nggak tahu, ngambek laptop saya. Jadi barusan saya lihat sudah selesai ngambeknya.
but now in English because some attendee also from Region 10 Region 10 area, Prof. Taufik, because Mbak Nia is very famous in Region 10 Asia Pacific.
Yes.
So they invite maybe Malaysia, Singapore, India, and many countries.
Okay.
So please continue in English. Okay.
Because, otherwise we will receive complaint from So Prof. Taufik. Please reply.
Pak Risnandar PhD, we already upgrade, and also Pak Mulyono Wijaya.
Could you please ask directly to Prof. Taufik?
Thank you very much, Bu Nia.
Yeah.
Yeah. Good morning,
could you please turn on the video?
Good evening. Yeah. Good evening, Pak Taufik. I'm from LIPI, and also I'm a former student of Pak Muhammad Taufik in Unpad.
Pak Nanda, could you please turn on the video? I'm sorry.
Sorry. I can see. I cannot access the webcam.
It's okay. No problem. Okay.
Yeah,
please.
as you explain about MISO and also DC to DC parts, how to get and how to buy in Indonesia, because I plan to develop some DC house in my village, some area in Sukabumi, maybe something like that.
Or maybe Prof. Taufik can send from Kalpoli.
Yes. Let's follow up. Let's follow up with email. Pak Risnanda, let's follow up.
You can drop email to Prof. Taufik, right?
Yes. Inshallah, I'll support whatever it is that you need when it comes to developing the DC technology, because you'll be the first, if this happens, you'll be the first person to be able to adopt DC technology.
Thank you very much, Prof. Taufik.
In a village scale, that would be good. That'd be good. So just follow up, please.
Yeah, thank you very much.
Yeah. All right. Okay, thank you. So now I would like to invite Pak Mulyono. Can we please ask directly to Prof. Taufik? I noticed you asked questions in the Q&A box.
Pak Dr. Mulyono Wijaya from BPPT, I think. Isn't it, Pak Mulyono?
Yes.
Okay.
Could you please turn on the video if you don't mind?
Ini teman saya, teman lama saya.
Iya, teman lama satu angkatan.
Ya, Pak Taufik, monggo kalau bisa turn on video, if it is possible for you.
Ya, Prof. Taufik, mengenai tadi about the DC house network of DC houses, how feasible is it to implement in an area? How wide is the region, and is it just the distance? Is because we know that transmission losses in AC network is smaller than DC network.
Yeah.
Thank you.
And also, I noticed you asked question how to handle losses due to transmissions.
Yeah. No, that's a good question. Yeah. Apa kabar, Mariana?
Baik, long time.
We came to the US at the same time, but he returned and I'm sticking around. Senang bisa ketemu lagi nih, Pak. So to answer to your question, for DC, you are right. When it comes to loss, it will be big if the area is, a certain area of the village, and so that's why in my presentation I mentioned that the DC house grid will only be suitable when you have clustered of houses, not dispersed, type of houses where one house and another house like miles away, like in Indian reservations. You've been in the US, so you probably are familiar with how it is with Indian reservation here in the US, where one house is miles away from the other house. If that is the case, then don't use the DC network. But when you have clustered houses, then definitely that's something that you can adopt when it comes to DC house. And I was going to say, in terms of the voltage level, somebody asked earlier, 48 is for inside the house, and we're sticking with that, right? But when it comes to the DC grid voltage, that's something that we are currently studying. So we don't know what that voltage is yet. So hopefully by the end of this year, not this year, but by the end of next year, we'll know what voltage to use for DC grid network. So it's still under study. Yeah.
Okay, thank you. Thank you, Pak Taufik.
You're welcome.
Mbak Nia, you are still mute, Mbak Nia.
You're muted.
Yes. Okay, thank you, Pak Mulyono and Prof. Taufik. Okay. I noticed Mas Grafika drop a questions. Do you want to ask directly to Prof. Taufik here, Mas Grafika? Hello, Mas Grafika. Are you there?
Yes.
Okay. Yeah, I saw you drop a questions. Maybe you can directly.
Thank you for the opportunity to ask directly to Prof. Taufik. I think, sorry if is it like a silly question, but sometimes I read that AC is more dangerous, but I have also read news that some people died because DC electricity. So is it true that DC is always safer than AC? Based on your experience?
I couldn't hear anything.
Sorry.
So
how about the safety, Prof. Taufik?
Yeah.
Because compare the DC and AC, and also some attendee says that the recent way we implement AC because this is the safety reason. It is true, or what is your opinion when we want to implement in the DC? How about the guarantee of the level of safety or so on? I think that is Mas Grafika or
sorry, because
that's a good question.
Connection.
So it's true and false at the same time. And it's true because I believe people learn about the fact that AC goes into the cycle where it crosses zero, right? It goes back to zero, whereas DC is always high, never crosses zero. So it's dangerous in terms of safety. It is dangerous, but to me, the perception of whether or not AC and DC, AC versus DC, which one is safer, I think it would lie on the available technologies, right? And these days we have the technologies that would make DC safe, right? With semiconductor technology, for example, right? We have all kinds of semiconductor technologies nowadays that can provide us with, fast reacting, protection system for DC. Yeah. For example, DC breakers. Right, DC breakers for AC makes sense. It's easy because you wait until the energy goes to until the signal goes to zero, and then you break the contacts, right? But in DC, how do you do that? Well, in DC, we have semiconductors to do that. So I think the technology is here and is rapidly advancing. You probably heard about GaN. Gallium nitride, silicon carbide, all of these different semiconductors that would improve the way we deal with DC. It is more challenging to protect, so that's true, right? It is more challenging to protect because, again, it is always high. It never crosses zero. But to me, that's, again, a golden opportunity, right? To me, I see it as a golden opportunity because then we can start exploring ways to be able to, reliably protect our DC systems. One example that we've done already at Cal Poly is protecting DC wires from arcing, right? If you have AC system with two wires, for example, if there's arcing between the two wires, that could easily be detected, and the protection system will kick in and it will trigger they'll trip the protection system. In DC, what we found is that it is not easy to do so. Right? When you have electrons, jumping from one wire to another wire when they're running DC, you could not see the difference in time domain. So when you look at the time domain signals of these, there is no difference between fault condition and a normal condition. So before you know it, if you still use AC solution for DC circuit, then pretty soon your house is going to be on fire, right? Because then you will not detect this arcing. But to me, that's a golden opportunity. That's why 5 years ago I looked at this as a challenge. And we got a grant from California, state of California, and we were able to develop the technology to actually detect arcing in DC and reliably, trip the breakers. And so that's just an example. And the technology that we use, I can share here, is that we don't use time domain, we use frequency domain. So when you look at the signals in frequency domain, you can clearly see the shift in the DC current, which is very interesting. Very interesting. In time domain, you don't see it, but in frequency domain, you can actually see that. So that's how we process the signals, and that's how we were able to, reliably protect the system. So that's just an example.
Okay. Maybe I want to continue the discussion, Prof. Taufik, because as you mentioned before, we are a first time to meet, isn't it? So I'm very because I think there is plenty of room we can discuss and we can cooperate together.
Yes.
Because my background is computer science, as for example, as you mentioned before, how to analyze in different domain, frequency or time domain about the pace of the related to the DC or AC. I think is need the algorithm, isn't it? And also about the smart grid, as you mentioned before. Actually, I also doing research in the smart city and so on. So, what do you suggestion about what type of contribution from the computer science people to, for example, to join or to make some
project, to join in this project.
Multi-discipline approach, so that maybe your idea, maybe your product will be, inshallah, will be more accepted in Indonesia, for example. Okay, please give us some. Okay.
Absolutely. Well, thank you so much. Yeah, thank you for your interest. We gotta start somewhere. We gotta start somewhere, and we don't have to walk. We don't have to run. We can, take a step at a time type of approach, right? I like it that way because then we can be more conscientious about what we are doing and more taking more feedback from different people. So let's just take a step ahead of every step of the time. We can start with maybe if you're interested, we can follow up with group discussion. Maybe you can find a group of students who are interested in these areas, on the software side of these areas, and then once you have that group, then we can follow up with maybe another meeting, right? A focus group meeting. That always has been my suggestion to other universities as well, not just here, to be able to follow up with a focus group kind of approach. And then we'll see from there, because this is just a 30, 40, maybe a 1 hour presentation from me. But when we get to discuss in more details, then hopefully there's where you will find whether or not this is a good match, for your future research, direction for your group. So let's start with that. If you agree, let's start with having a focus group discussion. Only people who are interested. That way we can get a more focused. What do you call it? More focus. What's the one? More focused task. More focused milestones. There you go. Right for this. Yeah.
Okay. Thank you.
Thank you, Prof. Taufik. Yes, I think time is up. Yeah, Prof. Wisnu.
How about the file presentation? Because
Prof. Taufik, is it possible for you to send the presentation file so we can distribute to the attendee, today's attendee?
Absolutely, yes, absolutely. I'll be more than happy to do that. I'll just email it to you. Yes. Yeah. Okay. Yeah, and I'm here until 8 o'clock here. So if you,
you're still at your office now.
No, I'm at home. I'm okay if you want to close this at what time is it there?
Oh, okay.
11.
Have time? Do you still have time, Prof? I think
it's okay because it depend on the Prof. Taufik. Is Prof. Taufik still have time? Because
I think
there is
we still
many questions.
Okay.
In the Q&A, and we will close in 11 in Indonesia and 8 o'clock in the California, isn't it?
Yes, that's correct.
Okay,
yes.
Okay.
Okay. So I'm going to ask you questions from current. I'm checking just now. Okay. From Mr. Badrus Zaman, yeah. How much DC energy can be produced from per meter roof?
How much
DC energy can be produced from per meter roof?
Oh, I see. You mean for solar panels?
Maybe.
Yeah, I'm not sure. For solar panels, that would depend on the location, right? Depend on the location of where you put the solar panel, depends on the angle of the sun. I know there's going to be an average number, but I don't have that number with me. For Indonesia, it's going to be different for other countries, right? So, yeah. So I don't know the answer to that. There's probably some information online for that one.
All right. Okay. So another question that's coming from Mr. Soli. Judin, how the DC source panel maintenance system that use as a power source in the home and multi-storage buildings? And also another question, how much loss percentage of CMO or MISO applications?
In terms of maintenance, if you talk about off-grid system, it will be the same, right? Because whether or not you use AC or DC, you would have to use energy storage if it's off-grid, right? So the maintenance cost usually comes from energy storage. That's the biggest cost, probably, energy storage. And again, as I said, it doesn't matter if you use AC or DC. If it's off the grid, you're going to have to use energy storage. So it's going to be the same. But what we calculated at Cal Poly, we actually studied this when it comes to installation cost rather than maintenance cost. Maintenance cost is about the same, roughly the same. Installation cost, what we found is that for the US, I don't know about Indonesia, I would guess it will be the same. Installing AC would be 50% more expensive than installing DC. So that's for installation cost. Right? So hopefully I answered your question. Maintenance cost about the same. Installation cost 50% more for AC roughly. Now, CMO and MISO. CMO and MISO. I think CMO, I don't know why do you want to use CMO for this kind of system. I'm trying to understand the question first. But MISO, the one that we developed, has an efficiency of 92-93% for 600 watt systems. So that's pretty high, 92 to 93%. And that's the advanced way of, that's the patent that we receive. That's 93%. If you use the simpler way, it's probably going to be less than 93%, probably going to be around 85%-ish. CMO, I would imagine it would be the same efficiency, even though, again, I don't know how you use CMO in this case. So it's going to be around 85%-ish to 90%, depending on the power level.
Yeah, alright, okay. Sekarang saya bacakan question dari bahasa Indonesia ya, dari PEMS, coming from PEMS. Ini Mas Hanif. Dari penelitian yang dikembangkan Prof Taufik tadi tentang DZ, how to integrate that system dengan AC dari PLN. Mas Hanif ini membaca ada beberapa penelitian similar. Jadi apa yang menjadi keunggulan dari penelitiannya Prof Taufik dibandingkan compared to other research, existing research?
Ya, jadi yang unik dari saya adalah dari solusi yang saya tawarkan adalah tidak memerlukan energi yang besar. Jadi energi yang kecil-kecil itu bisa kita manfaatkan. Ya, karena memang kalau kita lihat dari konteks listrik pedesaan, ini saya pakai bahasa Indonesia, nggak apa-apa ya?
Ya, nggak apa-apa.
Oke. Untuk konteks listrik pedesaan, kita kan harus paham lah, kalau di rumah pedesaan kan nggak perlu listrik yang besar-besar, ya kan? Mungkin mereka perlunya paling utamanya adalah listrik buat lampu, ya kan? Nah, lampu ini sekarang kan sudah semakin efisien, lampu LED misalnya. Dengan 100 watt aja mungkin udah ada 10 lampu bisa kan? Nah, jadi fokus saya itu adalah bagaimana kita mengembangkan teknologi yang berbeda dengan teknologi yang ada, dengan memfokuskan pada kemampuan untuk menerima, memfasilitasi satu atau lebih sumber energi yang skalanya kecil-kecil. Jadi fleksibel, dan juga bisa dari sumber daya manusia. Misalnya tadi saya sudah terangkan, misalnya kalau sekarang kan banyak yang suka main sepedaan tuh kan. Nah, kalau daripada main sepedaan di luar, ya udah main sepedaannya di samping rumah aja, nggak usah kemana-mana. Nah, itu sambil sepedaan kan bisa menghasilkan listrik buat rumahnya, itu loh misalnya. Atau permainan anak-anak kayak tadi yang ayunan dan sebagainya, itu kan kecil-kecil, levelnya kecil-kecil, kapasitas kecil-kecil, cuman nggak apa-apa. Kan yang kecil-kecil ini kalau kita satukan dengan MISO menjadi besar. Jadi itu mungkin keunggulannya, dan fleksibel. Nah, tadi saya udah banyak lah tadi urutannya. Fleksibel, reliable, accessible, dan sebagainya lah. Scalable. Gitu.
Yang belakangnya able gitulah ya.
Able ya. Itu scalable juga itu salah satunya. Jadi scalable itu artinya kita tidak memaksa. Misalnya satu rumah pengennya 50 watt, ya udah kasih 50 watt. Kita nggak boleh maksa, oh ini sistemnya harus 600 watt. Nggak boleh. Kalau menurut saya nggak boleh.
Stable gitu ya, sesuai gitu ya.
Sesuai kemampuan mereka kan, karena ini kan harus mereka bayar juga. Kalau mereka nggak punya dana untuk beli ya, untuk 150 watt, ya kasih yang 50 watt gitu kan. Dan ini ada segi edukasinya juga sebenarnya. Jadi mungkin ada banyak komunitas yang merasa tidak perlu listrik, ya kan? Masih banyak mungkin seperti itu kan. Buat apa listrik, bayar lagi kan? Ya udah kita kasih dulu, misalnya satu aja dulu, 20 watt aja dengan lampu misalnya kan. Itu kan murah ya mungkin ya, murah atau malah bisa disubsidi, nggak tahu. Nah dari 20 watt itu nanti mereka bisa merasakan manfaat kan. Oh ternyata malam-malam nih saya bisa pakai listrik ini nih buat anak-anak saya bikin PR misalnya atau apalah, atau istrinya apalah masak apa di dapur gitu misalnya. Dari situ mereka bisa belajar tentang manfaat dari listrik. Jadi tidak langsung kayak step change. Kalau istilah control system kan kita tidak boleh menerapkan step change secara sosial, secara culture gitu kan. Ini kalau bisa perlahan-lahan kita kenalkan listrik gitu. Nah ini salah satu caranya adalah dengan bottom up system. Jadi menurut saya ini perbedaan antara solusi yang saya tawarkan dengan yang sudah ada.
Ya, baiklah. Ya, ini ada pertanyaan dari Mas Yogi Ramadhani. He wants to start implementing solar energy in his house. Yeah. So, should he directly use 48 volts or 12 volts first? So, or maybe do you have any suggestion for him?
Ya, Pak Yogi dari Unsut ini pasti nih.
Oh gitu ya.
Betul ya. Jadi 48, kalau menurut saya 48 karena sudah kami pelajari ya, bahwa 48 itu yang paling ekonomis, paling optimum. Betul, dalam segala hal.
Bedanya, Prof.
Iya, optimum dalam hal.
Pak Yogi bisa di-upgrade Mas Hamid dari Unsut ya. Bisa tanya langsung.
Ya jadi ya sudah kami pelajari seperti itu. Jadi 48 volt itu sudah optimum untuk segala aspek dari sudut biaya, sudut ukuran kawat, sudut energy storage, kapasitas energy storage ya, sudut loss, daya yang hilang, macam-macam saya lupa. Saya ada ininya tuh laporan akhirnya. Jadi memang 48 yang kalau menurut saya 48.
Monggo nih Pak Yogi udah upgrade di panelis, bisa directly asking ini. Tadi juga masih ada pertanyaan kedua ya terkait bagaimana sistem proteksi ya. Monggo Pak.
Ya, Assalamualaikum Prof. Taufik. Kita ketemu lagi Prof.
Monggo.
Suara saya bisa terdengar?
Bisa. Ya.
Ini Pak, yang tidak saya tanyakan untuk sistem kalau di AC itu kan ada sistem proteksinya menggunakan MCB segala macam arrestor. Nah, bagaimana jika pada sistem DC di rumah, Prof? Sistem proteksi pada sistem DC aja.
Halo Prof Taufik, are you there?
Ya. Ya ini laptop saya masih ngambek lagi, nggak apa-apa. Yang penting masih kedengeran kan?
Ya, yang penting kedengeran ya.
Iya. Silakan kalau ada pertanyaan lagi.
Oh ya tadi barusan Pak Yogi nanya, mungkin bisa diulang Pak Yogi?
Oh nggak kedengeran.
Oh, oke.
Nah, saya ulang Prof.
Problem di laptop ya, ngambek tadi lagi.
Ngambek iya nih.
Ini Pak. Saya izin dalam bahasa Indonesia ya, Prof.
Saya tetap nggak dengar ini.
Oh, nggak dengar?
Nggak dengar.
Tapi kenapa dengar dari saya, Pak?
Itu dia. Nggak tahu, saya juga nih, bingung juga.
Pak Yogi, coba Pak Yogi diulang lagi.
Intinya bagaimana sistem proteksi di
nggak dengar.
Sistem DC.
Oh, intinya bagaimana sistem proteksi dari sistem DC ya, Pak Taufik?
Sistem proteksi?
Ya, sistem proteksi. Apa ini jangan-jangan kita hanya one way aja nih, Pak Taufik? Dengarnya cuma sama dari saya nih.
Kayaknya nih.
Ya. Bagaimana
ya, jadi,
Pak, sistem proteksi?
Ya. Tadi sudah saya jelaskan untuk sistem proteksi. Sekarang kita memakai teknologi semiconductor. Jadi sudah ada DC breaker. Sebenarnya udah dijual DC breaker yang teknologi lama, cuman mahal. Dan mungkin sudah ada yang jual di Indonesia mungkin ya, DC breaker. Jadi untuk yang breaker pakai DC breaker, atau kalau mau dikembangkan sendiri misalnya di kampus Pak Yogi ya, Jenderal Sudirman, itu silakan. Kami sudah kembangkan di Kapolri juga DC breaker yang pakai semiconductor. Jadi solid state DC breaker itu lebih cepat kalau DC breaker yang kami beli itu lambat ininya, responsnya lambat. Makanya kami tidak suka dan kami kembangkan teknologi solid state DC breaker. Terus fuses, kalau fuses kan sama saja, nggak perlu beda. Untuk DC fuse ada. Yang tadi arc fault itu kalau itu kan tambahan saja sebenarnya, tambahan saja. Jadi kalau kawatnya aman dari gigitan tikus, nah, misalnya itu saya pikir nggak perlu lah. Jadi kalau misalnya memang ada tambahan biaya untuk membuat arc fault-nya, interrupternya silakan bisa saya bantu. Tapi kalau untuk yang breaker bisa beli dan juga bisa dikembangkan sendiri, itu udah banyak kok ininya aplikasinya. Gitu.
Alright.
Terima kasih, Prof.
Ya, terima kasih. Ayo.
Yeah.
Oh ya, I noticed Mas Hamid tadi drop 2 questions in Q&A. Ya udah, Mas Hamid directly ask dah ke Prof Taufik. Silahkan Mas Hamid. Mana nih videonya?
Iya, video saya belum muncul juga kan ya?
Enggak,
ini
videonya Mas Hamid ini Pak.
Oh, oke. Kalau video saya udah muncul Bang?
Belum.
Oh iya.
Nggak apa-apa lah. Daripada, tapi dengar ya?
Iya, dengar. Sekarang kayaknya udah muncul nih. Oh, nggak juga.
Nggak juga, nggak apa-apa.
Oh, ya.
Ayo Mas Hamid, monggo. English ya Mas Hamid?
Okay, let me try. Okay, actually I have 2 questions.
Ini saya nggak dengar juga.
Oh, okay, sorry.
Nggak dengar Pak?
Iya.
Kalau tadi pas saya juga pas lagi koneksi juga kayaknya tadi.
I see.
Halo Mbak Nia, kalau Mbak Nia dengar nggak?
Dengar?
Oh.
Mas Hamid, speak louder please.
Yes, do you hear me, Prof Taufik?
Prof Taufik, can you hear Mas Hamid just now? Talking?
Halo?
Hello, yes?
Nggak, belum dengar.
Huh? How can you only hear my voice but you can only others?
Yeah. It's weird. I don't know.
Oke.
Gara-gara nge-freeze, Mbak Nia. Gara-gara freeze.
Oke, tapi saya bisa baca ini dari chattingnya. Indonesia has abundant.
Yeah.
Is that the one?
Yeah.
Indonesia has abundant renewable energy potential, solar, etc. But its utilization has not been maximized. What first steps can be taken to maximize this potential?
And another question also from him in the below, storage technology about the battery. Could you explain the advanced technology about the storage technology to support DC electricity system?
Yang pertanyaan, mungkin pakai Inggris ya. The second question, I don't think I could answer. I'm not an expert in energy storage. I'm not qualified to answer what technology is available right now for not just for DC, right? For AC, they're the same energy storage, right? It doesn't matter if you use AC or DC, they will be using the same energy storage. And I don't know the state of the technology for energy storage nowadays. I'm sure they're advancing, but it's not my expertise. I can't answer that. But for the first question, abundant. Okay, so what's the first step to maximize this potential? Ini pertanyaan yang sangat luas ini. so what do you call it? Very broad question. Maybe in the context of rural electrification, maybe. Because otherwise, this is a big question. So in the context of rural electrification, I think we need to be able to map, right? Map, and then based on which communities live where, we can then determine which type of solutions will be the best for these different communities. Because as I said earlier in the presentation, one size does not fit all, right? So for some communities, it may be that having solar farm will be the best to maximize the use. But for some other communities, if you have a more spread out, communities, different houses, between houses they're miles away, then I don't think solar farm would be the best. I think my solution would be better than solar farm if you have more dispersed communities, right? So having single residential DC will be better to maximize renewable energy. So to me, that would be the first step, right? Is to be able to, I'm sure that people already mapped the potential of solar energy in Indonesia, but the next step would be finding out which would be the best or the most suitable technology to be adopted at different communities in different villages, right? So I think that's the answer to your question. Again, I'm limiting the answer to rural electrification aspect of the question.
Okay. Or maybe a last question. Yeah, last question. Continue replying questions from Pak Yogi ya. Ini question from Mr. Daniel ya, because Prof. Taufik said that you propose 48-volt grid in the house. So I know that 12-volt DC lamps. Are there 48-volt DC lamps available, or do we need another converter for this 48-volt DC? What do you think?
Yes, the answer is yes. There are 48 volts LED lights. Mm-hmm. If not, we have the technology is already in such a way that we can actually build it ourselves. So you can actually build a 48 volt LED lights yourself. But if you want to buy them, they are available. I have 48 volt DC on my campus, and I bought them from eBay, I believe. So they are available. So yes, the answer is yes, they're available.
All right. Okay. Thank you, Prof. Taufik. I think time is up. 1 minute left from
okay.
Yeah, to 8 in your time. Okay. I think I'm sorry. Maybe still a few questions cannot be answered, but I hope all your answers to some questions could satisfy that question couldn't answer just now. Okay. Please give applause to all from participant to the Prof. Taufik. Thank you, Prof. Taufik, for your great talk today.
My pleasure. And
I'm also interested to join in your projects regarding in the last slide for mobile apps. So maybe another opportunity for recommendation system or anomaly detections to detect.
Yes. Yes, and also if I may, if any of the participants today is interested in knowing more about the DCS technology, feel free to contact me. I'll be more than happy to give a presentation for your institution in more detailed, aspect of the technology.
Yeah. Okay. Many participants asked about lecture material. Okay, we will distribute. Right, Prof. Taufik? You will send to us your PPT. Okay.
Yeah.
And then our team will send the materials to today's attendee. And also all participants, don't forget to fill the e-certificate if you want to request e-certificate. Maybe Mas Hamid, could you please share the e-certificate link in the chat box? Okay.
Yeah, of course.
Yes. Okay, for the e-certificate, you will receive a maximum 7 days after finish a series of these events, right, Mas Hamid? Yeah. Okay, thank you very much for all the attendees today. Can we have a group photo, Mas Hamid? But Prof. Taufik, can you turn on the video or cannot? You cannot.
I cannot. Yeah. Sorry.
Yeah, it's okay. No problems. Yeah, actually, I already took several screenshot. Well, okay.
Yeah.
Is there any news, Prof. Wisnu?
For the
tomorrow events. So we will still have one more event tomorrow titled on Education and Ethics in Digital Society that will be delivered by Prof. Lance Fong from Murdoch University, Australia. It will be delivered tomorrow at 1 p.m. Indonesian time. So all the attendees today, you are invited to join our last sessions tomorrow. Mas Hamid, could you please share the registration link for tomorrow event?
Yes.
Okay, in the chat box. All right. Thank you very much for your attention at this event today. Prof. Taufik, thank you very much for a great talk. Unfortunately, we cannot have a group photo together.
Yeah, no, thank you. Thank you so much again for inviting me.
Yes,
my pleasure.
Thank you everyone to attend and see you tomorrow for the attendee.
For our last event. Thank you. Stay safe.
Bye.
And
Thank you.
healthy. Bye.
Stay in health. Assalamualaikum.